Looking at section 3.2, I'm going to be dealing with the graph of a function. And so specifically looking at some graphs of different functions and asking several questions about those. Really just two main objectives here for this section. First, identify the graph of a function. That's pretty simple. We'll see there's a quick, easy test we can use to identify what the graph of a function is and if a graph is a function or not. And then the second one, obtain information from or about the graph of a function. That's where we'll really spend most of the time in this section working examples. And so just talking about graphs real quick. When we have real-world data, for instance, here's a table showing gasoline prices. Starts in the year 78 here, and then goes down, and then back over here to 91. And actually on the next page here, there's more data from 92 on to 2005. And that's just showing the different price of gas for those years. And looking at that data in the table, it doesn't really say a whole lot. I mean, there's numbers on there, and you can kind of look and see, you know, for an individual year what the price was, but kind of putting all that together as a whole, you don't really see a real good picture of the data, just looking at the numbers. But if you take that and actually make a graph of it, which is what we have here, you can see, well, now this makes a lot more sense, getting a big picture of the data. And so we can see here around 1980 there was a spike in the price of gas, and then that seemed to level off down to 86, and then more or less stayed level until here around 98 we see the price begins to go up. And so you know, graphs are really useful. They give us just a really good picture of the data, and you know, from that we can kind of see patterns and things like that. And so say all that to just say graphs are very useful, and I think everybody would probably agree with me on that. So how do we know if a graph is the graph of a function? Okay, that's the first question. We've got to go back to that definition of a function. Remember, when we talk about a function, we said the definition of a function is each input has only one output. That's the definition of a function. Each input has only one output. Now, if we go back to this graph here, what that means, remember, these down here on the x-axis, these values are the inputs. That would be the left column of the table. And then the vertical axis here would be the outputs. Okay, that's the second column in the data there. And so for each input we should have only one output. Really what that means is if we look at each data point for each year has only one price point. Okay, and I think you guys can kind of continue looking across there. As we go across, each year has only one price point. So in other words, each input has only one output. Okay, each horizontal value only has one vertical value, and so that means that is a function. Now there's a quick, easy way we can determine whether this graph is the graph of a function, and we'd use what's called a vertical line test. And so the vertical line test here says a set of points in the xy plane is the graph of a function if and only if every vertical line intersects the graph at most one point. So that's kind of stating the vertical line test. To kind of simplify that, if any vertical line crosses the graph at more than one point, the graph is not the graph of a function. So if a vertical line crosses at more than one point, not a function. So in practice, what does that look like? Okay, so I've got a set of examples here. We need to first determine whether the graph is a graph of a function using that vertical line test. Okay, so if it is a function, then we'll look at these questions here. So first, this graph right here is the graph of y equals x squared. Now that vertical line test, again, what that's saying, let me get a vertical line here. That's saying that this graph is the graph of a function if we can use a vertical line, and that vertical line only ever touches that graph in one point. And so I think, if I move this across here, you see that every vertical line only touches the graph at one point. Okay, I can't draw a vertical line that crosses that graph more than once. Okay, so this is a function. Okay, so so we do have a function there. So we need to answer the questions. What's the domain range, the intercepts if there are any, and any symmetry with respect to the x-axis, y-axis, or the origin. So let's take these one at a time, okay? So first, the domain and the range. Now, when you think domain and range on a graph, it's best to think in left boundaries and right boundaries. So for this graph right here, the domain, remember the domain is our x values. What x values show up on our graph? X values being the horizontal axis. So we need to ask, is there a left boundary and is there a right boundary for this graph? So for this parabola here. And the answer is no. If you'll notice, there's these arrowheads here, which means even though this thing's turning up, it's going to continue moving to the right and moving to the left. So there's not a left or a right boundary on this graph. That parabola continues to open up as it goes to the left and right. And so the domain, then, we could use intervals for that. If there's not a left boundary or a right boundary, it goes from negative infinity to positive infinity. For the range, we need to ask the same question. This time, looking at y values, we need to ask, is there an upper boundary and is there a lower boundary? And so, first, the lower boundary. If you'll notice, this graph touches the lowest point right there at a y value of 0. And since it does touch 0, we're going to include 0 as the left boundary, left endpoint there for the lower boundary. And then the upper boundary, I think you guys would agree, this graph continues to go up. So the upper boundary would be positive infinity. So there's our domain and range. Okay, part B, intercepts. Intercepts are where the graph crosses the x-axis or the y-axis. And so we need to ask, does this thing cross the x-axis or the y-axis anywhere? And yeah, it does. There's a point right there where it crosses both the x and the y-axis at the origin, which that point has coordinates 0, 0. So we just have that one point that is an x and a y intercept. Okay, the third question, we'll go back up here. We got the domain and range, we got the intercepts. Now it's asking about symmetry. So symmetry with respect to the x-axis, the y-axis, or the origin. And so this one's a little bit trickier. Symmetry, remember what symmetry is. If it has symmetry with respect to the x-axis, what that means is you should be able to think of folding this in half at the x-axis. And everything on one side of the fold should match up with something on the other side. Or you can also think of like a mirror image. This thing should have a mirror image on that x-axis there. Actually, this thing doesn't. Everything above the x-axis, there's actually not anything that matches up below the x-axis. So it doesn't have x-axis symmetry. Now the y-axis, though, it does have symmetry to the y-axis. You'll notice this piece right here. Let me do it like this. This piece right here does match up with this piece right here. So we can fold that at the y-axis and get that symmetry there. And so we do have y-axis symmetries on this graph. Now, what about symmetry with respect to the origin? That's the third part. What does that mean to have symmetry with respect to a point on the graph? Really what that's referring to is like a rotational symmetry. So if you were to put a pin right here at the origin and rotate this graph, so we actually want to take it and put a pin there at the origin and spin this thing. The question is, can you turn it less than a full turn and have the graph line up on itself? Okay, so we actually want to take this thing and rotate it, and there's not a way to make that happen. You can imagine if you take this U shape here and you rotate it around, you have to go a full circle around that point there at the origin before it lines back up. And so there's not any y-axis, any symmetry with respect to the origin there. So the only symmetry in this graph is with respect to the y-axis. Okay, next one, example 2. Is this a function? Now again, using that vertical line test, the question is, if we take a vertical line and go across our graph, does it ever cross more than once? And hopefully you see that that vertical line always crosses at one point, never crosses the graph more than once. So this is the graph of a function. So we have those questions again. First, the domain and the range. Looking at left and right boundaries for the domain. Even though this thing's turning down here, notice there's an arrowhead. Same thing up here going up. So even though this is turning down, it's going to continue going slightly to the left. Okay, and the same thing here. This is going to continue going slightly to the right. And so as far as a left boundary and a right boundary, there's not one. Continues going to the left and to the right. Same thing can be said. I think it's a lot easier to see as far as a lower boundary and an upper boundary. A lower boundary on this thing, it keeps going down. Upper boundary keeps going up, so the range is going to be the same. Part B, again, is asking about intercepts. Does this thing cross the x or the y-axis? Just like our last one, and we have one point where it crosses both the x and the y-axis. It's at 0, 0. Third question is the symmetry question. Does this thing have any kind of symmetry? Okay. First, with symmetry with respect to the x-axis, if you'll notice this piece right here doesn't really match up with anything over here. For y-axis symmetry, also up here for x-axis symmetry, if you fold this thing at the x-axis, this piece doesn't line up with anything up here. If you fold it at the y-axis, this piece doesn't line up with anything over here. So there's no x-axis symmetry, there's no y-axis symmetry. Now let's take a look at that symmetry with respect to the origin though. Let me erase some of this. If we take this graph and we rotate it, it's gonna rotate both of these, but just kind of go with me here. I'm gonna go a half turn. And if you'll notice, it's now down here, but doesn't that look the same as when I started? Okay, that picture here, when I rotated a half turn, looks the same, right? So because we can go a half turn and get that same picture, this does have symmetry with respect to the origin. And that's not the right thing. So yeah, this does have symmetry with respect to the origin. Okay. Example 3, is that a function? The answer is, let's check the vertical line test. I think you guys can probably already see what the answer is, but there's a vertical line that crosses the graph more than once. It means it's not a function. And you know that they actually drew in a line right there, just kind of illustrating that is not a function. And again, think about what that vertical line test is saying. Just to kind of reiterate this, they even gave us some coordinates for a couple of points. If we think about the points on the graph, 1, 1, and 1, negative 1, What do those 2 points actually represent? Well, that's a single input value of 1 that corresponds with 2 output values, 1 and -1. So I think it's clear to see that's a violation of the definition of a function. Single input with 2 outputs. So this is not a function. Since it's not a function, we're not answering any of those questions that we've been answering on the other two. We're finished with that one. Is this one a function? Okay, hopefully you see the vertical line that can be drawn. Again, crossing that graph more than once. So fails the vertical line test. This is not a function.